All right, good morning. Hope everybody's doing well. I want to talk mainly about strings and pointers and arrays and memory and all that sort of stuff today, and char star and char star star and stuff like that. This is going to be fairly detail oriented, and it's stuff that we'll do a lot of in CSE222 in winter, but we need to understand a little bit of it to do basic string manipulation and handling in C. So I want to get through some of this today, and I also want to talk about ODP 411 and the new ODP 411B. So we'll do a bunch of things related to strings and character arrays today. Let me turn off my chime for people coming in. All right, so let's start off something that I talked about yesterday in the first class and didn't get to in this class. This whole business of char star star, in particular char star star argv, is something that we see a lot in our main programs. Let me just try to demystify this a little bit. In general, we know if we say integer x, we're saying x is an integer, right? If I say integer star x, we're saying x is a pointer to an integer, but we're also saying x is an array of integers. How do we know it's an array of integers? Because we said integer star x. If I say float star x, x is an array of floats. So there's this general syntax in C. If we want to make an array of blah, we say blah star variable name. And there's a particular type of array we work with a lot, which is a character array. So if I say char star str, then str is an array of characters. And arrays of characters have another name, which is just a string. All right, so two things to keep in mind here. Blah star x means x is an array of blah, okay? And char star x means x is an array of characters or a string. All right, so now I want to think about this char star star argv a little differently. I want to think of it like that, right? Most spacing in C is irrelevant, so this is still char star star argv, but I'm thinking of it like this. And this would say argv is an array of char star. And since char star is the same thing as a string, this notation char star star argv is really saying argv is an array of strings. And that's what we really mean when we say char star star variable. We're saying that variable is an array. What's it an array of? An array of strings. And so that's why, for example, argv bracket 0, the first element of that array, is a string. It's a char star. And argv bracket 1, if it exists, is the second element of that array, and that element is also a string. It's a char star. All right, so that's how I think of the char star star. Split it up in your head and think of it. That second star says this is an array. What's it an array of? These things. A char star, which is a string. All right, I don't know how helpful that is in general, but that's how I think of it. So many things in C we can use without really understanding, and that's okay. But for me, I like having a reason why I'm doing something a certain way. I don't like just being told do it this way. So that's how I think of char star star. So pointer to an array of pointers. Pointer to maybe someone said in chat pointer to an array of pointers. It actually is an array of pointers, but argv itself is a pointer to a pointer. Yeah, we gotta be a little careful with the terminology array, but that's actually what I want to talk about after this is how arrays and pointers interact with one another, how they relate to one another, because they're almost exactly the same thing, but not necessarily for the reasons we might think. So we'll come back to arrays of pointers and pointers to arrays in a second. Let me talk about the ODP that you just did, and then the ODP that's posted right now to be done by tomorrow morning. So let's look at yesterday's ODP. So remember, yesterday we were trying to write a function named parse that takes a string, right, a char star, runs it through sscanf, checks to see if it's an integer between 1 and 4, and if it is, it returns that integer value between 1 and 4. If anything goes wrong, it returns -1. And the whole trick to doing this is to use sscanf. And so let's suppose we called our argument string str. We scan it with a %d. We save the result in some number. And so if str is equal to the string 1, 2, 3, so character 1 followed by ASCII code for 2, followed by ASCII code for 3, followed by a null terminator, we'll talk about those in a bit. Right, if this is the value of str, this call to sscanf says, okay, take this character array, 1, 2, 3, null terminator, and try to interpret it as an integer. That's what %d says. And it'll say, oh, that looks like the integer 123. And so it will take the integer value 123 and load it into this variable num. But if I had passed the string I23, which is not a valid integer, it does not assign anything to num. So how am I supposed to know whether or not the input was a valid integer? If I look at num after I call sscanf, it will have whatever value it had before sscanf. Now, some people just coded it like this, and they might have gotten lucky, because it may be that the initial value of num was not between 1 and 4. In which case, if you call sscanf and you check num, it's going to be equal to 0, it's out of range, you return -1, right? But in general, you have no way of knowing just from making this call whether or not this string was converted to an integer. There's only one way to know that, and that's to look at the return value from this function. And if I pass I23 to this, right, return in this case would be set equal to 0. If I pass 123, return will be set equal to 1. You gotta look at this. It's the only way to know if this is the integer corresponding to this string. Okay, so this will become abundantly clear in 411b. 411b, you're going to have to look at the return value from sscanf. But let's just look at sample code for 411. So there's a sample parse routine, right? Take your argument, which I called arg, run it through sscanf, ask it to convert it as an integer, store the result in a variable I. But let's save the return value from sscanf in this variable return. First thing you do, if return is not 1, then you didn't have an integer, return -1. If you get past this spot in your code and return was 1, then you did find an integer. Now let's see if it's in range. So if that integer, which we know is in I, is between 1 and 4, return the integer. Otherwise, it was out of range, return a -1. Alright, so that's 411. Let's take a look at 411B. So 411B, almost exactly the same as 411 with one extra detail, which is in 411, if your input was something like 123x, this would still return the number 123. Well, let's stick with our parse function. Suppose you put in the number 2x. Return will still be equal to 1, and num will still be equal to 2. The extra stuff after our valid integer doesn't change the behavior of this. Okay, so for the parse function you wrote for 411, this would be considered valid input just like this would. And here's why. sscanf really says, okay, let's start at the beginning of this character array and let's look for an integer. So it'll start here, it'll look at the 2 and say, well, that looks like it's an integer. Let's see what comes after it. It'll look at the x and say, oh, that's not an integer. Okay, I'm not going to look at the x, but I will look at the 2. That must be the integer value. And it'll convert that to an actual integer. It'll store that in num. It'll say I converted one thing, and it'll return a value of 1 as the function value. For 411B, we want to notice this, and we want to return -1, our error code. All right, so 411B, we want to say if the input is something like 2x or 2.3, let's return a -1, saying it's not a legal value. All right, so we have to do some work for this, and this is something we're going to use in future programming assignments to do really clean input processing, so that if the person's asked to enter an integer and they enter an integer followed by other stuff that's not part of an integer, we want to be able to notice that and say, hey, that's not valid input. Because in general, you know, if you're asking someone to type in a number and they type in something that's got extra stuff, it's a reasonable assumption to think that something went wrong. You know, they hit a key that they didn't intend to or something like that. We don't want to just assume, oh, you probably just meant, you know, the first part of that. We want absolutely clean input, or we're going to say, hey, try again. I didn't understand what you said.
Hey, Nick, I had a question about that.
Sure.
So for homework 4, we didn't need to handle those cases in particular, correct?
So homework 4 is peculiar. So when you're asked how many sticks do you want to take, if the person says something like, you know, 3, haha, or 3.5, or 3 space blah, you're supposed to just take that as a 3. Right? So just use sscanf the way we've been using it. Take it as a 3. Don't worry about the extra stuff.
Okay, I couldn't quite remember. Thank you.
Okay, but on the command line, right, if they say stick 25 ha, that's an error, right? Because the instructions explicitly say you've got to have either 0 or 1 arguments on the command line. But that's not an sscanf issue, that's just an argc issue. All right, so how do we detect that there's extra stuff after this legal integer? So there's a simple trick we can use, which looks like this. Same start, do your sscanf, give it the string that you want to read the characters from, ask for an integer, but immediately ask for a string with %s. And then let's have the address of our variable that we want to store the integer in. And then let's just have a bogus string that we're not going to do anything with. I'll just call it extra. So if I declare my variables, I'm just going to make extra, say, 120 characters. And when I do my scan, I'm going to say I'm looking for an integer followed by anything. Okay, and this has got to be a %s, not a %c. %s will match anything other than spaces. If there's extra spaces after my number, if there's a new line after my enter, which there often is, that will not satisfy this %s. Okay, but if there's anything other than spaces after my integer, that will match the %s, and the matching pattern will get stored in extra. Okay, so what does this do for me? Suppose my string is just 12. Okay, the 1, 2 will match my %d. That's an integer specification. It will get converted to an integer and get stored in num. So num will be equal to 12. It will then look for something other than spaces after that 2 to match with the %s. It won't find anything. So it won't do anything with extra, and it'll return 1. Why 1? Because it converted one thing, this %d. If my string is ha, it will start with the h, try to convert that to an integer. It'll say, nope, it's not an integer. It won't convert num, it won't convert extra, it'll return 0. Why? Because it didn't convert anything. It converted 0 things. If my string is 12 ha, it'll look for an integer, find the 1, 2. Yep, I can convert that to an integer. It'll set num equal to 1. And then it will look for a string, a set of characters following that 2. It'll find HA. Yep, that matches a %s. Extra will be set to HA. Return will be set to 2. Why? Because it converted 2 things. It set 2 values in my output side. Okay, so we can use this one function call to know exactly what our situation is. And the one case where we have a valid integer and nothing else is this case right here. And the trick is make sure that return is equal to 1. So use the same logic that you used on ODP 411, but just throw in this extra piece on your sscanf. Try to scan something after your integer, save it in a dummy variable that we're going to throw away, and make sure return is still equal to 1. If it's equal to 2, you had extra stuff. If it's equal to 0, you did not have an integer at all. If it's equal to -1, your string was empty. So the condition that tells you that you had exactly a valid integer and nothing else is return equals 1, which is what you should have been doing in ODP 411. So make sure return is equal to 1. And if it is, then num has the value of that integer. Alright, so that's our sscanf trick. So scan it like this, do a %d, %s, put in an extra variable here to hold the extra stuff, and then make sure that nothing matched that extra stuff. And again, if there's white space, if there's a new line, that won't get loaded into extra. Your return will still be equal to 1. So almost exactly the same code as 411. Just one extra tweak on your scan. Does that make sense? And it's worth mentioning there is a potential security issue here. %f is not inherently the safest thing to use in a scanf or an sscanf. Okay, %s exposes you to a possible buffer overrun. If my string had, a billion characters in it, then this %s could, take a billion characters and throw it into extra, right? But if I know this string is well behaved, if I know it has a null terminator somewhere before, the 120th character, then I'm not going to have a problem with that. But %s by itself doesn't limit how many characters will get stored in here. So always be a little suspicious if you use a %s with a scanner, like scanf or sscanf. Possible vulnerability there. Not a problem for this course, because I won't try to hack you. Alright, so that's a trick, and we'll use that a lot in our C code this quarter. Whenever we want input to be validated as an integer, we'll do something like this to make sure it's an integer and there's nothing else after it. Doesn't come up in homework 4, okay? As we already said, homework 4, just use plain old sscanf with a %d to read an integer. But for 411B and then for future C assignments, right, we'll come back to this. All right. Make sure you do the quiz online. A few people have done it already. It seems to take about 5 to 10 minutes for most people to do it, but it's due tomorrow. So make sure you do the online quiz. Okay, it's an scanf versus sscanf exercise. Okay, let's talk about arrays in C. So arrays in C cause a lot of confusion. And arrays inevitably get us to talking about pointers, which gets us talking about memory. If you've had Engineering 270, this may make more sense. Okay, or if you've done assembly language in any way, shape, or form, this may make more sense. This is one of these areas where even though we're working in a higher level language, we need to be thinking a little bit about what's going on at the hardware level. Okay, and this is going to be more and more the case as we go through this course and we move on to 222 in particular in winter. We're going to be needing to think about what's going on at the hardware side of things. Okay, so let's talk about arrays. So, the idea of an array is we have a bunch of data that somehow belongs together. For example, the grades on an assignment, or a set of phone numbers for people in some organization. We have a bunch of data that we want to treat as kind of a single unit to be able to pass it around from function to function and so on. And so rather than have, a bunch of separate variables, we have one variable that somehow gets us to a bunch of data. Okay? And so if we have an array called x, we can get to the elements of x by saying x bracket and then something that we call an index. All right, in C, arrays always start with index 0. That's super important, and it's super freaky if you're not used to it. And eventually it becomes the way that you view the world, right? You think of everything as starting at 0. And it makes a lot of things work better than it's starting at 1. But as humans, we start counting from 1 usually. Computers usually start from 0. So x bracket I means the element at index I, okay, which is actually the I plus first element if we were to describe it to a human. All right, so how do we set up arrays in C? Well, there's two ways. I can say integer x bracket 10, and this is a declaration, okay? If I just say x bracket 10, I'm asking for the element at index 10. But when I say integer x bracket 10, I'm declaring to the compiler that x is the name of an array of integers. And I'm also declaring that I want it to hold 10 integers. So I'm telling the compiler that somewhere down the road I might talk about x bracket 0 or x bracket 5 or x bracket 9 or anything in between. Okay, I won't talk about x bracket 10 because that would be an 11th element. And if x holds 10 integers, the indexes of those elements go from 0 through 9. Okay, so that's the index 0 thing. All right, so the usual way we set up an array in C is to say type of stuff we're storing in the array, name of the array, bracket, size of the array, number of things in it, close bracket, semicolon. All right, that's a declaration of the array. And we declare our array so that the compiler knows what to do when it sees something like this. All right, but there's this other thing that we'll see sometimes, which is integer star x. And this is technically also a way to declare an array in C. After we say integer star x, we can say x bracket 5, and the compiler will take that to be the 5th element, right, element 6 actually, but the element at index 5 of an array named x, where x was declared right here. All right, but there's some differences between doing this and doing that. So the thing with C is the way that arrays are implemented are really like this. Okay, so this is a pointer, right? We do pointers in 121. This is saying x points to an integer. Okay, x is the address of an integer. And so let's make a picture of the computer's memory. So here's the memory. And remember, memories are addressed. So here's the address in memory, and here's the contents. And your memory, if you have 16 gig on your machine, it's got 16 billion addresses, and each address has 8 bits associated with it. All right. And your memory may be bigger because we have virtual memory and good engineering 250 stuff like that. Okay, so let's say integer x bracket 10. I'm telling the compiler I want x to be an array. I want it to be an array of integers. I'm also telling the compiler I want it to be an array that's big enough to hold 10 integers. And when I do this, the compiler, together with the linker, part of the compiler basically, will do the following. It will find somewhere in memory that's big enough to store 10 integers. And let's say that starts at location 2000. And it will set aside enough space to store 10 integers, starting at location 2000. So location 2000 is where x bracket 0 will be stored. Now integers take 4 bytes, so the next integer is not going to be stored at location 2001. It'll be stored at location 2004. And the next integer will be 2008. And if we're going in hex, the next integer will be 2000C. And the next will be 2010, and so on. And it will find 10 consecutive locations that can be used to store the 10 integers of this array. All right, here's the really fun part. After it does this, it will set the variable x equal to 2000. So the value of x itself is the address in memory where the array begins. All right, so in this case, x would have the value 2000. That's also the address of x bracket 0. But if it knows x starts at location 2000 and it wants to find x bracket 1, it knows it just has to add 4 to this and look at location 2004. That's x bracket 1. If it wants x bracket 2, it adds 8 to 2000, 2008. That's where x bracket 2 is. So it does this index math while your program is running to get to a particular element of this array, because x is equal to the address where that array begins. Okay? So x is not the value of x bracket 0. It's the address of x bracket 0. Okay? That's one thing to keep in mind. The next thing to keep in mind to notice here is that there is nothing in what I've described here which tells the system when it's running that x only has 10 integers. Because if I ask for x bracket 100, what will the system do? It will take the starting address for x, it'll add 100 times 4, and say, oh, that's the element at location 2400. And it'll go off and it'll read what's in that location, and that'll be what it gives me for x bracket 100. So arrays don't have inherent lengths in C. All right, if we're managing our data and we know that we've only got 10 integers in there, I'm not going to ask for x bracket 100. Okay, but remember, we use arrays to store strings because strings are not a native type in C. There's characters, integers, doubles, floats, and so on, and there's arrays. Strings are arrays of characters. So I have a character array, char str bracket 10. There's nothing I can do in my code to know that there's only 10 characters associated with this array. So we use a trick. When we store a string, like HI exclamation mark, well, this would get stored in str bracket 0. The I will get stored at str bracket 1. The exclamation mark will be stored at str bracket 2. We add an extra terminator at the end. We have this thing called a null terminator. It's ASCII code 0, and we store that right after the last character of our string. And it's purely a convention. When we say printf %s, str, the code inside printf will look at this location, the first thing in the array, and print an H and an I and an exclamation mark. And when it sees this, it'll say, I'm done. And it'll stop printing. When we say, what's the string length of this variable, calling strlen, it'll say, oh, let's see, you got 1, 2, 3 characters. Oh, that's the end of the string. Your string has a length of 3. But it's just a convention. Okay, it's a necessary convention because there is no inherent length to arrays in C. All right, so let's look at this difference between two ways of approaching strings. And this comes up when we write code. Sometimes we do this, sometimes we do that. We got to know when to do which. Okay? The main difference, two differences. One, this is asking the compiler to set aside 120 spaces, right? Enough space to store 120 characters. And two, it's setting str to the address of that first spot in memory. This does neither of those things. This is simply saying str is a pointer to a character. But it does not give str a value, and it does not set aside any memory anywhere to store characters. Okay, this is a declaration. This is really an initialization and an allocation of memory as well as a declaration. Okay, this simply declares str to be a character pointer. This declares str to be a character pointer, and it says find me a spot where there's 120 spaces available, and it says set str to the address of that first spot in memory. So this is doing a whole lot of extra stuff beyond this. Alright, so let's look at some of this in code. So let's make a string array. Alright, so I'm going to say char str bracket 120. I'm going to call fgets to read from standard in. That's my keyboard. Save up to 120 characters of input into this array str, and then let's print it out. Okay, pretty straightforward test code. So I can say hello, and it tells me my string's equal to hello. And there's an extra new line at the end, right? Because we know fgets tacks a new line on the end. So that's fine. Let's do the following. Let's not do an fgets, and let's just print out str without actually doing an fgets. So I'll say char str bracket 120, and I'll just print it out immediately. And str equals, well, nothing, I guess. And that seems to be pretty consistent. But if I try this on a different machine, I might get a very different result. Alright, we'll come back to that. Let's try this. Let's print out str as a %d. So I'm going to say char str bracket 120, then I'm just going to print out str as a %d. And it'll warn me that that's not a good thing to do, but I'm going to ignore that warning. And str has this crazy value, 178338896. And every time that I run this, str has a different bizarre looking value. So what's going on with that? Remember, when you do this declaration, three things happen. You declare str to be a pointer to a character. You ask the system to find space for 120 characters. And then you ask it to set str to the address of that first character in memory. So this declaration up here is actually initializing str to be a location in memory. In particular, the location where the first of 120 open locations can be found. So there's a better way to print pointers, which is a %p that changes the format to hex. And if we're on a 64-bit system, it will print this as a 64-bit number. So 8 hex characters gets you 32 bits, so 64 hex characters. And it will suppress leading zeros. So let's compile this. And let's run go 1. That's the value of str. Okay? And at some point, you'll start to recognize this as a valid memory location. Usually things that start with 7F or 7FF or something close to 7FFFF, those are valid memory locations. They're in an area of memory called a stack. Okay, if you've done 270, we talk about stacks. We're looking at something pointing to the stack on an x86 machine. And it changes slightly from run to run. But you notice it's the same ballpark. It's always starting with a 7FF, and it might be an FD or an FE or an FC or an FF. Okay, so STR is an address. And if I were to print the address of str bracket 0, it's exactly the same thing as the value of str. All right, now let's try this instead. Let's just say char star str. Well, it tells me my string is nil. All right, well, what does that mean? Let's go back to printing as a %d. It's equal to 0. So when I say char star str, I'm declaring str will be a pointer to a character, but I'm not initializing it. And its default value is just 0. Right? When I do this, it's changing the value of str to some memory address, and at that memory address, space has been reserved for 120 characters. But like this, it's just a pointer to a character, but it doesn't have a particular value. In fact, it has the value 0. Which means if I go ahead and I try to use that as a string, I'm going to get a seg fault. Why? Because fgets is being told read up to 120 characters from my keyboard and store it in memory starting at address str, which is 0. Well, 0 is not a valid memory location. It's set up deliberately to be an inaccessible location so that if you mess up and you don't initialize something, instead of just writing into memory, you'll get a seg fault. So seg fault's basically a memory access error. All right, so when do we want to use char star? Well, we want to use it often when we're dealing with functions. All right, so let's make a function called count that takes a pointer to a character, that's a string, and returns an integer. And let's go ahead and use fgets to read in that string, and let's call our count function. And print out the value. So let's declare our count function here. So integer count. And I'm just going to say it takes an argument called arg, which is a character array. And let's count how many characters are in this. Let's count how many spaces are in here. Alright, so we're going to count the number of spaces in this input line. So I'm making a for loop here. I'm going to use the string length function on the string, which tells me how many characters are in the string, right, up to and not including the null terminator. And for each character in this string, I'm going to see if that character is equal to a space. And if it is, I'm going to increment a counter. So I'll initialize this counter to 0. I'll count up how many spaces, and I'll return that number. The details of what this count function is doing are not really important. I just want some sample code here that will take in a string and do some processing on it. All right. And then I want to just look at why we're using a char star. So this is fun, and it returns 2 because I had 2 spaces. There's 6 spaces, so it finds 6 and so on. And if I just hit enter, there's no spaces. Alright, so don't worry about the for loop down here for now. What's happening here though with passing arguments? In my main program I had to declare string bracket 120 or some number because I wanted to set aside space for characters, and I wanted str to be the address of that first character in memory. So I passed that to fgets, that's fine. I also passed that to my count function. My count function does not need to set aside space in memory for a string. It's receiving an argument which presumably already points to a chunk of memory. Right? When I call count, I'm passing str. str is the address of some location in memory where I have characters stored. So down here in count, I don't need to say count arg bracket 120, and I wouldn't want to, because I don't know how big my array is, I don't know how much memory there is, and I'm not asking for new memory to be allocated. All I need to know is that the argument coming into this function will be pointing already to somewhere in memory. So here, all I need to do is declare argument to be a character pointer. Right? So that's a case where this is sufficient. Just tell the compiler this is pointing to a character. But in the main program that's calling this, that's where I needed to set aside actual memory and say point to that location in memory. But when I call str, if str is 4000, when I get down here, arg will be 4000. And when I say arg bracket I, it'll be the element at index I in that array that was set up way up here in my main program. Alright, so that's the main interplay between char star and char variable bracket, some number. Right? This is allocating space and pointing to it. This is saying, hey, arg already has been allocated and is already pointing somewhere. I just want to use it. So more often than not, but it's not a hard and fast rule, in our functions we're just going to do char star. Whereas in, say, a main program, we're going to do a declaration like this. And again, this is not something you really necessarily need to understand, you know, to this level of detail yet. We can use it kind of mechanically, but we want to be building our understanding of how this stuff works, because it's going to be critical for CSE222. To be able to know what's going on at the hardware level and in the memory of the system when we write this code. So for ODP 411B, right, I've already given you the prototype for parse, and you're just going to assume that you have a character array and you can just access the elements directly, but you don't have to deal with the elements, you just have to pass it to sscanf. Alright, that's the end of our time. That's everything I wanted to get through. So tomorrow we're going to go back and finish up our discussion of VI, give you some time to work on these things. We'll talk about 411B if there's questions on that. Homework 4 questions if you have them, but we'll wrap up VI, and then we'll move on to going deeper into some C programming. Alright, so I will see you tomorrow. Have a good afternoon.